So now we will discuss about a boundary layer, but we focus on the turbulent boundary layer. So we focus on power law form. So the idea is, okay, so as I said in previous chapter, if we have a flat plate like this one, so we have a flat plate like this, so and then when we have a free stream velocity, so first it will create a laminar boundary layer, so and then it will have a transition region here, so and then it will change into fully turbulent. So normally in textbook when it says the turbulent here, it is 100% turbulent. So and then we will discuss these three situations actually. So now in chapter 4, so we are discussing about the fully laminar boundary layer. So and then now and then in chapter 5 we discuss about the transition. Now we are discussing about the fully turbulent boundary layer, which is we assume all the boundary layer is turbulent. There are no laminar and there are no transition. Then also in this chapter, in chapter 6, we will discuss what happens if our situation is like this. Means a part is laminar boundary layer and another part is turbulent boundary layer. Turbulent boundary layer. What kind of calculation can be made? Okay, so this is the syllabus. Okay, so just a recap from the laminar boundary layer. We know that the velocity profile at laminar boundary layer can be shown like this. So we have the power 1 quadratic. So we have the third order polynomial. We have a quartic by the power of 4. And we have the sinusoidal. And also we learn how Blasius calculate this calculation in terms of numerical. So this is the idea. And for turbulent boundary layer, so we have two methods. Okay, one is called power law form, and another one is called empirical form. So therefore, power law form, it's quite easy. So it's easier compared to method number 2, but it's less accurate. So and then for method number 2, so it is a little bit complicated, but I will show you the simple one because it complicated because it should be calculated by numerical. So you need to have a program to calculate everything from the value that you have. So but I show you the for the range that we could calculate by in exam. So and then because it is complicated, so it is more accurate compared to the method number 1. So okay, so this is the basic diagram of flat plate and a boundary layer. So again, so this is the equation for the Reynolds number, rho UL over mu. And mu here is the dynamic viscosity of fluid. So it also can be written as UL over nu, which is the nu here is the kinematic viscosity. Okay, so and then, okay, so we go for the first method. We call it as a power law form. So why we call it power law form? Because we assume the velocity profile in the turbulent boundary layer can be shown as this kind of velocity distribution. So we have u over u. So in my handwritten, I will write as u over u with bar here, just to differentiate the small u and capital U. It is equal to y over delta by the power of 1 over n. And this value of n here, the integral of n here, is depend on the velocity, the speed, or the Reynolds number that occur on that plate. So for example, if this we take the common transition, so 5 times 10 by the power of 5 to Reynolds number 10 by the power of 1 by the power of 7. So the value is n is equal to 7. And if it's by the power of 8, so you take an 8, and by the power of 9 here, you will take n is equal to 9. Okay, so this is why we call the power law form, because we assume that the velocity profile, it can be represented by this basic equation. Okay, however, so the calculation is actually totally similar with the von Karman calculation for laminar boundary layer. Okay, please bear in mind that for von Karman, it can be used for turbulent and also laminar. But for Blasius, okay, so it only can be used for laminar. So for von Karman, it can be used for laminar and also turbulent. Okay. So if you remember, in a laminar boundary layer, if we calculate laminar boundary layer by using von Karman equation, first we have von Karman equation, tau is equal rho u square d theta dx, and then we equate with the shear stress tau from the Newton viscosity of law, which is equal to mu du dy. Okay, so we have mu here. Okay, actually, so but okay, this is the turning point, the important part in turbulent boundary layer. In turbulent boundary layer, we cannot use the idea of Newton law of viscosity. Why? Because in Newton law of viscosity, we have terms of mu du dy at y equal to 0. Okay, so it is because when, for example, we have u over u equal y over delta by the power of 1 over 7 here, if we derive its du dy, so we get this term. Okay, that's okay. The mathematics is correct. But if we substitute the value of y equal to 0, so we get du dy is equal to 0. Yes, the mathematics is correct. But the problem is this mathematical answer is not reflecting the real situation. Okay, that's not about the mathematics is not correct. The mathematics is correct, but it cannot be used because in logic, the value of tau must be exist. Because why boundary layer occur? It is because they have resistance. So the tau is exists. Suddenly we calculate the tau is equal to 0, then means that this equation cannot be used in turbulent boundary layer. Okay, so the problem is if the Newton viscosity of law here cannot be used, so means the shear stress from the von Karman here cannot be solved because we have two unknown parameter, which is the value of theta here, which is in delta later on, and the value of shear stress. So means this equation is remain unsolved. But we could calculate the value of shear stress relationship by using the analytical method by Blasius. Okay, so I'm not going to show this one. Okay, but this always give in the question. Okay, because the Blasius shear stress relation here is actually conducted by using a numerical or by the experimental works. So so that's why it cannot be derived by equation. And usually we will give the value of shear stress in the question. So means that to solve turbulent boundary layer, means you need to know how to start your derivation from the von Karman, and you equalize with the value of shear stress by Blasius. Okay, please do not use shear stress by Newton law of viscosity, because it will ruin your calculation, because the shear stress will equal to 0. Then you will get everything is 0. Okay.
Doctor, excuse me.
Yes.
I have a question for this equation.
Okay.
So when we see a velocity profile like this one,
Okay.
to the power 1 over 7,
Okay.
That means we have a turbulent.
Yes.
Directly.
Yes.
So we cannot use the shear stress for Newton law of viscosity.
Yes.
Directly, we will choose this question,
Yeah.
okay, to and equate it with the von Karman equation.
Yes.
From this equation, from equating this equation, we will get a sigma.
Yes.
Thank
You
you.
get that. Okay, delta, not sigma.
Delta. I'm sorry.
Okay. Yes, that's correct. Okay,
Thank
I
you.
will show you the example.
Okay. Okay.
Okay. So this is the main idea that you need to remember. Okay. Okay, uh, let's say we are calculating the boundary layer thickness delta, and we assume that our u over u here is equal to y over delta to the power of 1 over 7. Okay, so and then what we start with the von Karman equation. So von Karman is showing like this. So we have tau rho u square d theta dx. Okay, and then you are advised to write like this. So rho u theta d over dx for the theta. Okay, that's sometimes the equation like this one is could confuse students. So it is the same meaning with the d dx of theta here, and this theta can be calculated by using this common equation. So I think previously you could I teach you how to calculate the value of theta. So the equation of theta is integral 0 to delta u over u 1 minus u over u. So substitute u over u here with uh, y over delta to the power of 1 over 7. So you get 7 over 72 delta. So you substitute here. So rho u delta. So you have 7 over 72. And then you will have d delta over dx. Okay, so you will have this one. Okay, so and then start here. What you need to do is you need to solve like laminar boundary layer, but the difference is you cannot use the Newton law of viscosity. So this is we have a mu here. Okay, I will change the notes later on. Okay, so uh, you cannot use this Newton law of viscosity because it will give us the value of 0. So what we need to do is we need to equate with the Blasius shear stress from the Blasius calculation. So this will be give in the question. Okay. So and then so it is given that for 1 over 7, so the shear stress is equal to 0.0226 rho u square mu over rho u delta 1 over 4. But in certain textbook, they will give you as nu u delta with 1 over 4. So you need to understand that this is nu, which is kinematic viscosity, and this is mu, which is the dynamic viscosity. So we have a mu equal rho nu. So please remember the idea of viscosity. So and then what we need to do is we equate. So this is the shear stress from the von Karman, and this is the shear stress from the Blasius. So we equate these two equations. So and then what we do is we bring all the delta, the term of delta on the left side, and we bring everything on the left side here. So and then what we do is we integrate both terms. So we integrating both sides. So finally we could get this term. For sure, we have the integral constant here, and then we substitute the boundary condition. So I think it is familiar for you about the boundary condition. So if x equal to 0, delta is equal to 0, then the value of c is equal to 0. Now our equation is become like this. So and then we could simplify this term. So we get delta is equal 0.3721. So and then the best way to show the value of delta is to represent them in by using the Renault number. So in this case, you will have 0.3721 x over Reynolds number to the power of 1 over 5. So this is the way we calculate the delta, the boundary layer thickness for the turbulent. So this is just the representative of the turbulent. So then the calculation is exactly the same with this laminar boundary layer. So I hope I could go a little bit faster here. So we know that U over U is 1 over 7. So and then we could calculate the value of delta, because first we calculate the value of delta star here by using this equation. Then we get is 1 over 8 by the power of 1 over 8 delta. We substitute the value of delta with the previous equation that we have here, and then we could get delta star is equal 0.0465x over Reynolds number to the power of 1 over 5. So this is the momentum thickness. Previously, I also show you how to calculate this one. So you need to substitute the value of U over U here, and then we get 7 over 72 delta. We substitute the value of delta here, so we get it is 0.036x over Reynolds number to the power of 1 over 5. Okay, and then the shear stress. So for shear stress here, please use the shear stress that given by Blasius, because the shear stress from von Karman, tau is equal rho u square d theta dx, is not completely solved because it still has term of d theta dx. If you want to use it, it is okay, but you need to do the integral first. You need to bring the, okay, you equate this value with a certain one. You need to bring the x to the difference, the left side. So and then you need to integrate both side to get the value of theta and x. So I think this is a very long way to go. So you are advised to use the value of shear stress tau here from the Blasius, because the Blasius here everything is in equation. So there are no dx, d delta and so on. So by having this one, so we substitute the value of delta here. So and then we could get the tau here is equal 0.0289 rho u square by the power of Reynolds to the power of 1 over Reynolds to the power of 1 over 5. Okay, so and then the drag force here. So as I said in the first slide in chapter 4, so the reason why we take care, we do study about boundary layer, about it is because we want to know more about the drag force, the lift force as our final product of the boundary layer. So mean the greatest effect of the boundary layer is the existence of drag force and the lift force. Okay, the lift force and drag force here, we need to calculate it by using the integral. So the common equation is the integral from 0 to L tau times b dx. So why we need to integral? Because we need to understand that the increment or the value of the shear stress for every point along the x-axis, along the L-axis is different. Okay, so means the value of here, shear stress at here is different and so on. So we need to integrate in terms of dx here. Okay, so that's the first idea that you should know, because normally student will make mistake. So because they assume that, okay, tau times A will give you force. So and then they will calculate the shear stress here, the value of shear stress times with area. So finally you will get force. Yes, you will get force, but that's not the drag force. The drag force should be start with the integration, because the increment of drag force depends on the velocity profile. It might be can increase linearly, it might be increase exponentially. Okay, so it's depend on the velocity profile. Okay, so we have the integration of tau b dx. So b dx here will refer, b here is the width of the plate. So this is the plate. So B here is the width of the plate, and dx is the x-axis length. Okay, so why we start with the dx here? Because, for example, we have a plate here. So we are start in calculating a very small area. So this small area will have certain value of width. So if we have the idea here. So we are calculating this area first. So the width is B, but the distance here is dx. Okay, that's why we do the equation here as B times dx. Okay, so now we substitute the delta, the shear stress here by this equation that we get from the previous calculation. So we have B, we have X. So here dx. So here for Reynolds number here, you expand this Reynolds number. So Reynolds number is equal to rho u x over mu. Okay, now we have X here. So you could integrate with dx here. And finally, you will get this term. Okay, so here the limit is 0 to L. So mean you substitute the value L here to the X that we get from the integration. So now it's appear as capital L. Okay, it's not appear as X anymore because you substitute with value of L here. So I think it's okay. It's very simple integration. You could do this, okay? But the turning point is you need to expand the value of Reynolds number. If not, you will say that okay, there are no X here, okay, because tau there are no X here. B is also no X, so integrate with X, so it will become only one X. Okay, that's not the idea. Okay, you need to expand the Reynolds number. So finally, you will get this FD here is equal to 0.0361 rho u square BL and Reynolds number of 1 over 5. And then we could calculate the drag coefficient. So the drag coefficient, previously we know this is the equation. So it normally we write as FD is equal CD times 1 over 2 rho AU square. So now we could get the value of CD by dividing FD with the 1 over 2 rho U square BL. So and then we know that the FD from the previous calculation is like this one. So we could neglect the value of BL. We could neglect the value of rho U square here. So we could calculate the CD is equal to 0.0722 over Reynolds number of 1 over 5. Okay, so this is the calculation of the drag coefficient. So here, please be careful. If you write C with capital D here, this is actually the drag coefficient. Drag coefficient. So which is means that the total, mean the drag coefficient for the whole plate. Okay, and if you see it is a C with a small d here, so it is about the local drag coefficient. Okay. However, this symbol is quite not a fixed one. You need to be very careful when you read textbook. In certain textbook, they will use C with the small f here because f here will reflect you the friction, the local friction. So the local means if you have a flat plate here, so this CD is actually about the coefficient for one single point here. So and then the relationship is tau is equal to C small d 1 over 2 rho u square. So there are no A because you know if we multiply tau with A, so we have multiply the right side with A, so tau times A will get the force. So this will become drag force and our equation will become this one. CD, the CD here, C small d will change into C capital D to reflect the total drag force. Okay, so this is the idea to by the power form, okay, to calculate everything, the boundary layer thickness, the drag force, the coefficient of drag force of fully turbulent boundary layer. So the first method is by assuming the let's say it's 100% turbulent here, by assuming the velocity profile in the turbulent boundary layer here is u over u by y over delta by the power of 1 over 7. Okay, so means that it can be changed 1 over 6, 1 over 7, 1 over 8, or 1 over 9. Okay, but the common one. So, as I said, Blasius, okay, normally the delta is equal to 5x over square root Reynolds number here is the representative equation for laminar boundary layer. So means that if you don't have any velocity profile for laminar boundary layer, it's okay for you to solve the problem by using this equation, by using any equation that's come from Blasius, the delta, the theta, the CD, and so on. And also for the turbulent. For turbulent, if the question didn't give you any velocity profile, so you don't know whether it is 1 over 7, or 1 over 8, or 9, it is okay to use 1 over 7 as your representative value for the fully turbulent boundary layer. Okay, because normally in normal speed and so on, for our application, for our car and so on and so forth, it is quite suitable with 1 over 7 condition. If more, so it is we need a high velocity to create that Reynolds number. Later on in our discussion, I will show you about the higher Reynolds number, because application for this one is actually more about the lift force later on.